Alrighty, so today we're going to be doing a problem with capacitance and capacitors. So for those of you following along, we're on problem number 69 in chapter 16 of our book, and we're on page 565. So I will read out loud the problem for you, and the problem refers to these two diagrams if you'd like to follow along. So capacitor C1 equals 6.0 microfarads, and capacitor C2 is 2.0 microfarads. And they're charged as parallel combinations across a 250 volt battery. The capacitors are disconnected from the battery and from each other. They are then connected positive plate to negative plate and negative plate to positive plate. Calculate the resulting charge on each capacitor. So, that is this situation diagrammed here. Here is our battery, and you want to be careful with the symbols because the battery symbol looks quite a bit like the capacitor symbol. But the battery symbol will have one line longer and one line shorter. Capacitor should have both lines about the same length. So what's going to happen is our 250 volt battery is going to turn on. It has a positive and a negative side. And what's going to happen is the electrons that were already present in the plate of the capacitor, because the capacitor starts off as neutral. So there is a balance initially of electrons and protons on each of these metal plates. And what's going to happen is the electrons are going to be pulled from those plates because across the potential difference of the battery, and they will move over to the other side. And so this right side here will become negatively charged, and this left side here will become positively charged. And so what we want to look for is based on the capacitance of each capacitor and the voltage, we want to figure out exactly how much charge initially is on each capacitor before we start doing weird stuff by combining them. So capacitance is a measure of how much charge you can store across a given potential difference. So what we can do is we can use this formula here to solve for the charge on each capacitor. So let's do that right here. Q1, the charge across on capacitor C1 is equal to C1 times our voltage, which is 250 volts. We'll leave that as a variable for now. And so that is equal to 6.0 microfarads. Keep in mind that a microfarad is 10 to the negative 6th normal farads. 6.0 microfarads times 250 volts. And now it's calculator time. 6 times 250. And then we're going to divide that by 10 to the 6th to get our unit conversion. And that is going to be 0.0015 coulombs. And what that means is that if this were capacitor 1, right here, this has a positive end and a negative end. That means that on this negative end is negative 0.0015 coulombs. And on here is positive 0.0015 coulombs. Just like that. So then we'll go ahead and continue our calculation to find the charge on capacitor number 2 and Q2, very similar procedure. It's going to be 2 microfarads times the 250 volts. 2 microfarads times 250 volts. Don't forget to make sure you account for the microfarad and not a normal farad, and that will give us 0.0005 coulombs of charge. So that is the initial charge across both of these capacitors. And right now those capacitors are separate. So then, once the battery is disconnected, it will be rewired, and you could draw the rewiring any way that suits you, and this is how it's drawn at the moment. So we see that the negative end of capacitor 1, the negative plate, is connected to the positive plate of capacitor 2. The positive plate of capacitor 1 is now being connected to the negative plate of capacitor 2. And what's going to happen now is since capacitor 2 is initially negative on its negative plate, electrons are going to go from this negative plate to the positive plate of capacitor 1. The electrons from the negative plate of capacitor 1 are going to move now to the positive plate, of capacitor 2, and they'll be pushed along by our Coulomb forces, and they're going to try to balance themselves out. And so the way that they're going to balance themselves out, let's just look at this positive-negative interaction right here. So we have a negative plate right here, and that's going to be connected to this positive plate on C2. So negative plate is being connected to positive plate, and this is our negative capacitor on C1, and the charge on this plate initially is negative 0.0015 coulombs. Negative 0.0015 coulombs. And this is from capacitor 1. And now on capacitor 2, once they're connected, this plate initially has a charge of positive 0.0005 coulombs. And so what's going to happen? You may have already guessed, these charges will balance out, and it will not make the whole thing neutral, it'll just make it balanced out. So what's going to happen is the charge will balance out, and it won't just be equal across capacitor 1 and capacitor 2, because the capacitors themselves are different. We know that they're different because they were given different capacitance values initially. And so since C1 has greater capacitance, we already know that capacitor 1 is going to be able to store more charge. So after this interaction occurs, the charge will not balance out evenly. Capacitor 1 will still have more of its charge. And so we know that since capacitance is proportional to the area of the capacitor, and the charge it has is proportional to the area of the capacitor, it must be that the charge is proportional to the capacitance. And we will use that aspect to make a proportion and determine and calculate just how much charge is distributed to each of these capacitors. So let's go ahead and do that right here. So capacitance 1 over capacitance 2 is equal to the final charge on 1 divided by the final charge on 2. Since capacitance 1 divided by capacitance 2, there's a difference of 3 here. We know that that will equal 3. And the units will cancel out because microfarad divides microfarad, and so this is actually literally just equal to 3. So since Q1 over Q2 equals 3, we also know that the sum of the charges on Q1 and Q2 must be equal to the sum of the charges that was there initially. That's your conservation of charge. So the sum of charge that was there initially is taken from adding these two amounts. And so negative 0.0015 plus 0.005 is going to be equal to negative 0.001 coulombs. So Q1 plus Q2 must add up to negative 0.001 coulombs, and we have another equation that relates Q1 and Q2 to be 3, and so now we just have two equations, two unknowns, and we can go ahead and solve those. So Q1 equals 3 times Q2, so then I will substitute in 3Q2 as Q1 because I can. 3Q2 plus Q2 equals negative 0.001 coulombs. Therefore, 4Q2 equals negative 0.001 coulombs. Therefore, the charge on capacitor 2 at the end must be equal to negative 0.00025 coulombs from dividing it by 4. Negative 0.0025 coulombs is kind of a gross way of writing that, so I'm going to move over here and rewrite that a little bit. So Q2, the charge finally on capacitor 2 after they are reconnected in this kind of weird way is going to be, and we're just going to look at the magnitude of it, because keep in mind on the other end, this was capacitor 1 is negative, capacitor 2 is positive, but there's also another plate where capacitor 2 is negative and capacitor 1 is positive. And the measure of the charge across the capacitor, remember, sort of keeps that as the same and combines them together to form and describe the total charge that is stored over the capacitor. So Q2, the magnitude of that, and we're going to turn this into its absolute value of 0.25 millicoulombs, because a millicoulomb is equal to 10 to the negative third coulombs. And therefore, Q1 must be equal to, since they are Q1 divided by Q2 is equal to 3, Q1 must be 3 times Q2. I'll write that out over here. Q1 equals 3Q2. Therefore, Q1 equals 3 times 0.25 millicoulombs. Therefore, Q1 is finally 0.75 millicoulombs. Q1 is 0.75 millicoulombs. And that is our final answer. Right there. Alrighty, so I hope that was helpful, gave you a little better understanding of capacitors, how charge moves through capacitors, and how they interact with batteries. And I'll see you next time.